Alright, in this video we're going to be looking at exclusive and independent events. So if we have events that are said to be mutually exclusive, these are events that cannot happen at the same time. For example, say you've got a coin. We can define event A as you flip the coin and you get heads, right? And we can define event B as you flip the coin and you get tails instead. Events A and B are mutually exclusive because there is no way that you can flip a coin and get heads and tails at the same time. And so this makes these two events mutually exclusive. However, on the other hand, we say that two events are independent when the occurrence of one event does not affect the probability of the occurrence of the other event. We're going to look at a few examples just now, but in general, if events A and B are independent, we can say that the probability of A intersection B is equal to the probability of A times the probability of B. So this equation will be used a lot in proving whether events are independent or not. So let's look at some past paper questions. Here we're given two ordinary fair dice, one red and the other blue, are thrown. Event A is the score on the red die is divisible by 3. Event B is the sum of the two scores is at least 9. Part A, find the probability of A intersection B. Alright, so what we can do here is we're going to draw a possibility space diagram to just show the range of possible outcomes. So we've got one red die and we've got one blue die. So it's a fair six-sided die. So 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. So I'm just going to put dots at every possible combination of events that can occur. Then we're going to figure out which outcomes represent event A and which outcomes represent event B. Alright, so these are all the possible combinations of outcomes that we can have. We need to find the outcomes that represent event A. That's the score on the red die is divisible by 3. So I'm going to circle that in red. Divisible by 3. Okay, that's going to be this row as well as the row at 6. Alright. So we can even create a key at the bottom to explain. Event A is denoted by a blue circle surrounded by a red circle. Alright, and then we want event B. Event B is the sum of the two scores is at least 9. Alright, so in this column, the highest sum we can get is 1 plus 6, which is 7. So there's nothing there. In this column, the highest we can get is 2 plus 6, that's 8. So there's nothing there. And in this column, the third one, at least 9, we get a 9 here. And then let's go to the column for 4. 4 plus 4 is 8. 4 plus 5 is 9. So this would be event B. This is event B. Alright, let's go into the next column. We've got 5 plus 4, that's 9. 5 plus 5, that's 10. 5 plus 6. And then the final column, we're going to have 6 plus 3, that's 9. Then we've got 6 plus 4, 6 plus 5, and 6 plus 6. And on our key, event B is going to be a blue dot surrounded by a green triangle. So we can say that event A intersection B is going to be a blue dot surrounded by a red circle, which is surrounded by a green triangle. Okay, so now we can go on to part A, which says find the probability of A intersection B. So according to our key, A intersection B is a blue dot surrounded by a red dot surrounded by a green triangle. So that's going to be 1, 2, 3, 4, 5. 5, and this is a 6 by 6 grid. So that's a total of 6 times 6, outcomes 36. So A intersection B is 5 out of 36. Now part B says, hence determine whether or not the events A and B are independent. If A and B are independent, we know that independent, if I can spell that correctly, we know that the probability of A intersection B must be equal to the probability of A times the probability of B. So we've already found the probability of the intersection. Now let's find the probability of A and the probability of B. So let's start with the probability of A. So event A is a blue circle surrounded by a red circle. So that's the whole row here at 6. So 1, 2, 3, 4, 5, 6. And the whole row at 3, 7, 8, 9, 10, 11, 12. And we said our total outcomes are 36. And then the probability of event B, that's a blue circle surrounded by a green triangle. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10 out of 36. So we can substitute into our equation and check that the probability of the intersection is equal to the probability of A times the probability of B. So we said our intersection is 5 out of 36. So this should be equal to the probability of A times the probability of B. So 12 over 36 multiplied by 10 over 36. Okay, so let's check what our right hand side simplifies to. So that's 12 divided by 36 multiplied by 10 divided by 36. That is 5 over 54. And 5 over 54 is not equal to 5 over 36. So this means events A are not independent since they do not satisfy that equation there. So you can conclude that therefore A and B are not independent. So this is how you prove whether events are independent or not. Let's look at one last example of a different style question on independent events. We're given that there are 400 students at a school in a certain country. Each student was asked whether they preferred swimming, cycling, or running, and the results are given in the following table. Alright, a student is chosen at random. Part A, find the probability that the student prefers swimming. So the student prefers swimming is this column over here. That's going to be 104 plus 31. So the females plus the males out of the total number of students, which is 400. And so that simplifies to give us, this is 104 plus 31 over 400. That gives 27 over 80. Okay, so that's our final answer for part A. Now part B says determine whether the events the student is male and the student prefers swimming are independent. Justify your answer. Okay, so let's label the student is male as event A. The student is male. And let's label the student prefers swimming as event B. The student prefers swimming All right. If events A and B are independent, then it means that the probability of A intersection B must be equal to the probability of A times the probability of B. Alright, so we need to find all of these probabilities. So let's start with the intersection. That's the student is male and prefers swimming. So if we go to our table here, the student is male and prefers swimming is this cell in our table. So probability of A intersection B is going to be 31 out of 400. Okay, and then let's go on to the probability of A. The probability of A, the student is male. Okay, so that's going to be the bottom row. The sum of this bottom row, which is the student is male. So that's 31 plus 57 plus 92 out of a total of 400 students. So if we simplify this, the probability of event A, that's 31 plus 57 plus 92 divided by 400, that gives us 9 over 20. And event B, the probability that the student prefers swimming, we evaluated that in part A, that's 27 over 80. Now let's check if our equation is satisfied. So the probability of the intersection, 31 over 400, must be equal to the probability of A multiplied by the probability of B. Alright, so let's check what our right hand side simplifies to. So on the left we've got 31 over 400, and then on the right we have 9 over 20 times 27 over 80, which gives us 243 over 1600, and this is not equal. So it means that therefore A and B are not independent. And so this is how you prove or determine whether events are independent or not. And that's it for this video. Make sure to go through the quiz, and I'll see you in the next video.